In question 10, we're presented with a diagram of a right circular cone. The top portion of this cone has been extracted to form a basin. We are given several measurements here. The radius of the original cone is 15 centimeters. The radius of the base of the basin is 12 centimeters. And the slant height of the basin is 10 centimeters. In the first part of the question, we must show that the length from B to E is 40 centimeters. The key to solving this is observing that we have some similar triangles in our cone. Let's focus on the triangles ABC and DBE. Both of these triangles have a right angle. They also share a common angle at B. And since the angles in a triangle always add up to 180 degrees, we can deduce that the third angle must match also. Since these triangles have the same three angles, we say that they are similar. A useful result about similar triangles is that the ratios of the corresponding sides will always be equal. In this question, we were asked to find the length of BE, and I've labelled that here as x. I've also written in some of the measurements that we were given. DE is 12 centimeters, AC is 15 centimeters, and EC is 10 centimeters. In the triangle DBE, the side opposite the right angle is x. The side opposite the angle at B is 12 centimeters. So the ratio of these two sides is x over 12. Since our triangles are similar, we know that this will be equal to the ratio of the same two sides in the triangle ABC. Well, in that triangle, the side opposite the right angle is x plus 10, and the side opposite the angle at B is 15. So the corresponding ratio is x plus 10 over 15. Now we have an equation which we can solve for x. To begin, we can multiply both sides by 15 times 12. Then we can multiply the brackets on the right. 12 by x is 12x, and 12 by 10 is 120. As the next step, we can group our x terms together by subtracting 12x from both sides. 15x minus 12x simplifies to 3x. And as the final step, we can get rid of the multiplication of 3 by dividing both sides by 3. When we perform the calculation, we see that x is equal to 40 centimeters. In the second part of the question, we must find the total internal surface area of the basin. Well, this area will consist of two components. The flat circle at the base of the basin, which I've coloured in orange, and the curved surface around the interior of the basin, which I've coloured in blue. Finding the orange area won't be too bad. All we have to do is find the area of a circle. However, the blue area is a bit more troublesome. To find this, we should look back at the original cone. If we find the total surface area of this full original cone, and then subtract away the curved surface area of this smaller cone, which I've coloured in red, then that will leave us with the desired blue area. Now that we've outlined our strategy, let's go ahead and actually calculate each of the areas. The first result we need to use is that the curved surface area of a cone is equal to pi RL, where r is the radius and L is the slant height. The original big cone had a radius of 15 centimeters and a slant height of 50 centimeters. Subbing these values in gives us 750 pi. The smaller cone, BDE, which I had coloured in red, has a radius of 12 centimeters and a slant height of 40 centimeters. Subbing these in gives us 480 pi. As I mentioned earlier, the curved surface area of the basin is obtained by subtracting these two figures. When we do this, we end up with 270 pi. To find the flat surface area at the base of the basin, we'll use the result that the area of a circle is equal to pi r squared, where r is the radius. We were told that the radius at the base of the basin was 12 centimeters. If we sub this value in, the area comes out as 144 pi. Now that we know the curved surface area and the flat surface area, we can find the total surface area of the basin by adding these numbers together. When we do this, we end up with 414 pi. We were asked to give our answer correct to 1 decimal place. Converting this to a decimal and rounding to 1 decimal place gives us our final answer of 1300.6 centimeters squared. In part 3, we must draw the diagram of the net of the curved surface of the basin. We must include enough measurements so that no further calculations are required to draw the diagram with a ruler, compass and protractor. The following fact is useful when tackling this question. The net of the curved surface area of a cone forms a sector of a circle. Let's go ahead and illustrate this idea on the cone we were given. Imagine that we grab a pair of scissors and cut a straight line from C to B. Then, if we unfurl the cone and push it down onto a straight surface, we'd get a picture like this on the right. The line, which we cut with our scissors, will appear on the boundaries on either side. The base of the basin, which I've drawn in as this pink circle, will correspond to an arc. The top of the basin, which I've drawn as a blue circle, would also correspond to an arc. The curved surface area of the basin will be the region between these two arcs. I've coloured that in grey here. Now that we've got the sketch of our net diagram, we need to make sure we label it with enough measurements so that it could be accurately drawn. From the previous parts of the question, we already know the side lengths. BE measures 40 centimeters and EC measures 10 centimeters. Adding these together tells us that BC is 50 centimeters. These side lengths are useful, but they don't paint the full picture. To be able to draw the diagram, we would also need to know the angle at the base of this sector. I've labelled that in as theta. To finish off this question, we'll need to figure out what this angle is. A useful fact here is that the curved surface area of the cone will be equal to the area of the sector in the net. I should emphasise that we're looking at the full cone here, not just the grey region for the basin. Well, in the last part of the question, we found the curved surface area of the original cone. It was 750 pi. If we equate this to the area of the sector in our net, this will allow us to solve for theta. If you consider the full 360 degrees of a circle, the area of the circle is pi r squared. If you don't have the full circle, but instead have theta out of the 360 degrees, well then you'll have theta over 360 of the area. So the formula for the area of our sector will be theta over 360 times pi r squared. The sector that we drew had a radius of 50 centimeters. We can sub this value in for r, and then simplify to obtain an answer of 2,500 over 360 times theta times pi. Since the area of the sector must be equal to the curved surface area of the original cone, we can equate this value to our 750 pi and then solve for theta. Since both sides of our equation are being multiplied by pi, a good first step is to divide both sides by pi and cancel these out. Focusing on the theta, it's being multiplied by a constant, 2,500 over 360. To get rid of this multiplication, we should divide both sides by this number. Performing the calculation on the left brings us to our answer here. Theta is 108 degrees. In part B, Seamus is picking a new 4-digit PIN code. We're told that each of the digits must be between 1 and 9 and that no digit can be used more than once. In the first part, we must work out how many such codes are possible. It's useful here to consider choosing the code 1 digit at a time. We can visualize this by drawing out 4 empty boxes and then thinking about how many valid ways there are to fill in a digit to each of the boxes. Focusing on the first box, we have 9 choices for what we could write in, namely the digits from 1 to 9. When we consider filling in the second box, we're going to have 8 choices. This is due to the fact that no digit can be used more than once. Whatever number we put in the first box will be blacklisted and no longer available for use in the second box. By the time we move to the third box, we've already used 2 of our 9 digits, 1 for the first box and 1 for the second box. This means that there'll be 7 choices remaining for the third box. In a similar fashion, when we reach the fourth box, we've already used 3 of the 9 digits. This means that there'll be 6 choices left over when we're filling in this final box. To get the total number of choices here, all we have to do is multiply together the number of choices for each individual box. This gives us 9 times 8 times 7 times 6, which comes out as 3024. In part 2, we must work out how many of these codes contain the digit 2. A nice way to approach this is to try and find the number of codes without the digit 2. This can be done in the exact same way we worked out part I. We'll lay out 4 boxes for our code and think about the number of valid choices for each box. Since we don't want to allow the digit 2, we're going to have 8 choices of digit for the first box. 1, 3, 4, 5, 6, 7, 8 and 9. Similar to part I, each successive box will have one fewer choice than the previous box. This is due to the fact that we're not allowed repeated digits. So each time we write a digit in the box, it rules that out as a choice for future boxes. So the total choices for the number of codes without the digit 2 will be 8 by 7 by 6 by 5, which is 1680. In part 1, we saw that there was 3024 total codes. We found that 1680 of these do not contain the digit 2, so the remaining 1344 do contain the digit 2. In the final part of the question, we need to figure out how many of the codes have the sum of the first 3 digits equal to their 4th digit. The first thing to observe is that most of the time, when you add together 3 digits, you end up with a 2-digit answer. For example, if you added 4 plus 6 plus 7, you would get 17, which is a 2-digit number. If we want the first 3 digits to sum to the 4th digit, this implies that the sum must be a 1-digit answer. And there's not too many ways this can happen. We're also working with the restriction that we're not allowed to repeat digits, and that just restricts the possibilities further. In fact, there's only 7 valid ways you can add together 3 distinct digits and end up with a 1-digit answer. I've listed these here. 1 plus 2 plus 3 is 6. 1 plus 2 plus 4 is 7. 1 plus 2 plus 5 is 8. 1 plus 3 plus 4 is 8. 1 plus 2 plus 6 is 9, 1 plus 3 plus 5 is 9, and 2 plus 3 plus 4 is 9. We have to be careful here. Our final answer won't be 7, and that's because we have to consider the ordering of the first 3 digits. As an example, consider the sum 2 plus 3 plus 4 is 9. We have to think about how many different ways we can arrange the 2, the 3 and the 4. If I start with the 2, there's 2 options to finish off, 3, 4 or 4, 3. If I start with the 3, there's also 2 options to finish off, 2, 4 and 4, 2. In a similar way, if I start with the 4, we again have 2 options to finish off, 2, 3 or 3, 2. In total, we have 6 distinct codes being generated from our sum. So, putting everything together, we have 7 different sums, and each one generates us 6 distinct codes. The total number of codes will simply be 7 times 6, which is 42.